he's done some really nice scanning tunneling microscopy work looking at superconductors that he's going to tell us about. He did his work with Seamus Davis, PhD work at Cornell, where he's learned how to brave the cold weather in cold systems. And he's headed off to much warmer and sunnier places at UC Davis soon as professor.
Thank you very much. Thank you, everyone, for coming to this talk. And thanks to the Hoffman Group for also coming and supporting me out in front here. I've been to a few of these talks, and I've noticed that they have a bit of a more pedagogical bent to them. So hopefully I'd like to bring you along the journey of my own work, why I think it's important, and how I view physics, and why I can continue to do what I do. Let me begin by thanking my collaborators. Most of this work, actually all of this work was done at Cornell. So these are the collaborators that I work with at Cornell to bring you this work. This is Kazuhiro Fujita, who's now at Brookhaven National Lab. Steve Atkins, who actually is now at Stanford as a postdoc. Many of you know Seamus. We had some theoretical help from Michael Lawler, Una Kim, and some wonderful collaborations with Subir, who is here. Let's start with the time period in which we had the scientific revolution and see what it is that actually brings us those revolutions. So we'll start with van Leeuwenhoek here, who is acknowledged to be a father of microbiology. And he did that by creating a new way to make lenses, very small lenses, which have very great magnification. And by doing that, he was able to see for the first time muscle fibers, bacterium, and spermazoa. And Hooke even described them as being the shoulders on which all of microscopy stands at that time. At the same time, or very close, sorry, actually a little bit before that, you have Galileo, who was trying to increase the magnification of the telescope. And by doing so at the time, about a factor of 30 over the best telescopes at the time, he was able to see in September of 1610 the phases of Venus. And he noticed that the phases of Venus actually look very similar to the phases of the moon. And he said, well, how could this be possible unless the heliocentric model of the universe is correct, not the geocentric version of the universe? So by being able to develop a visualization technique, he was able to take one of the biggest ideas of the time, heliocentric versus geocentric, and find scientific evidence showing that it pointed to the heliocentric version. We come to modern day, and now we're looking at the early universe. So back in the 1960s, Penzias and Wilson found that there's a hum to the universe. There's this, what looks to be a uniform cosmic microwave background radiation. At the time when they looked at it, it was a remarkable discovery, first of all. But when they looked at it, it looked very uniform. And it wasn't until much later with the probes such as COBE and WMAP that they were actually to map out the variations to within 1/10,000th of a degree Kelvin in the night sky. And what they were able to see is that looking back into the primordial universe, you can start to see the origins of clusters and galaxies. So by being able to visualize, we are now coming back to seeing how the universe gets the structure that it does. You look at solar events and you have ultraviolet visualizations in the different wavelengths. Then you can start to tease apart, for example, how the processes in a star generate solar flares. Turbulence and fluid mechanics, still one of the big problems in physics, can be imaged by, for example, in this technique, putting a colloidal suspension in the fluid and then being able to directly visualize this. What you're seeing here is a turbulence transition, whereas fluid is flowing and it's starting to shed vortices. I love this image. This is from scanning confocal microscopy, which is able to reconstruct a three-dimensional object by looking at different planes. And since they're different distances apart, so what you're seeing is the anaphase of a cell going through division. And you're seeing these spindles which are starting to pull away the chromosomes. And amazingly, what you see is there's one that's lagging behind. So if the cell is supposed to be healthy, you have to have the same number of chromosomes on either side. So this is a wonderful image in case you were able to then look at this cell afterwards and see if it has some defects, where those defects could have risen from. And close to my own heart is scanning tunneling microscopy. And this is an image of iron atoms which have been arranged in this particular pattern on top of a metallic surface, and they create confinement for electrons. And in particular, what's very fantastic is you can see the wave nature of electrons in this system. As the electrons are confined, they're going to scatter and set up standing waves. So by direct visualizations, you're now able to see the wave nature of matter. So as I go along this talk, I'm going to talk about some of the techniques that I've worked on in the last several years. I'm going to talk about the CUPRATES, high temperature superconductivity, and also some of the connections that we're going to try to make between condensed matter physics and how we can answer some bigger questions in physics. I'm going to start with the question, what is a superstate? Because we're going to be finding a technique to how to image these superstates. I'm defining that as a macroscopic quantum condensate, and that's a quantum mechanical object which has an amplitude, which is defining its density, the number of particles, for example, that are sitting in this macroscopic quantum phase, and also this gauge breaking quantum phase. So for example, in a superconductor, this was a U1 breaking phase. In case of the Higgs field, this is SU2 cross U1. So there's many objects that can become a macroscopic quantum condensate, and I'll give you a few examples later. We know bosons, if you have a number of them at high temperatures, they might be occupying different energy levels, and if you lower the temperature, bosons can actually all occupy the same energy states. And we call this process Bose-Einstein condensation. So all particles will occupy macroscopically the same wave function in the system. Fermions have to do something a little extra, and they have to pair up to make something that's like a boson. So at high temperatures, you have fermions. They have occupation of many energy levels. And if you get them to pair, then they can behave like bosons and then condense again into a macroscopic quantum phase. The discovery of these phases really goes back to the early 1900s. And at that point, there was no quantum mechanics, or just the inklings of quantum mechanics were being discovered by Cameron Owens, who saw or his graduate student probably saw, a drop in resistivity in mercury. And at the time, they really didn't know what it was. They just saw that the resistance dropped in this object. Later on, we discovered that this is actually a fermionic superconductor, one in which a spin up and the spin down pair in an L equals 0 angular momentum state. 20 years later, almost 30 years later, you have the discovery of superfluid helium-4, which is rather remarkable because Cameron Owens used helium-4 to cool his samples, but they never actually looked at the flow of the liquid itself. And in this case, you have a bosonic superfluid. We move forward a little bit, and then we get to the other isotope of helium, helium-3, which is a fermion. And this is the first observation of a superfluid, which is no longer L equals 0, but L equals 1. It means the pairing of the two fermions actually has a L equals 1 angular momentum. We call this a P-wave superfluid. We move into the era of cold atoms, and you have superfluids coming in rubidium-87, and then also the fermionic versions in superfluid potassium-40. If you were now to look on a large scale at macroscopic quantum condensates and look at the temperature scales at which you find them, we'll find that actually it's a rather large scale, over 25 orders of magnitude. So first we start with these mercury compounds back in the 1900s. Kapitsa and Allen find superfluid helium-4. We're down to the microkelvins now with superfluid helium-3. And then in the mid-1980s, you have the high temperature superconductors. And we're going to focus on these a little more. Of course, then the cold atoms come around, and then we're getting down into the low microkelvin and close, you might be starting to approach the nanokelvin temperature range. But on the other side, there's now a lot of evidence that perhaps when you look at compact stars, so neutron stars, for example, that there is both proton superconductor properties and neutron superfluid properties. So if you look at the cooling of these objects, you see that they're cooling a lot faster than you would expect. And the models say that the superfluidity actually opens the new channels for neutrinos to be able to leave the systems, and they're carrying the heat with them. There are also theories that quarks can condense. So you have a quark-quark condensate. And the newest condensates that has been discovered, that little blip right there, which got awarded the Nobel Prize, is the Higgs boson, which comes from the Higgs field. There's a wonderful paper written by Frank Wilczek on this universal condensate, the Higgs condensate, And what's important here is that as a condensed matter physicist, our field has been studying condensates, as I said, for over 100 years. And so we've learned something. And at this point where now particle theorists and particle experimentalists are getting into their own condensates, we're hoping that a collaboration can emerge in which one can exchange ideas. One thing I'd like to say here, because we all learned that the Higgs boson gives rise to mass. Well, it really gives rise to the mass to the W and the Z boson. So if I ask you what gives rise to mass and matter, what would you say? Well, Einstein gives the answer. When you look at the nucleus, which is made of nucleons, protons, and neutrons, they're made of quarks and gluons, which keep them together. Those things comprise less than 10% of the mass of the nucleus. The rest really comes from the fact that you've pushed them into a bound object, and then there's motion. And Einstein said that if you have that energy is going to be equivalent to some kind of inertia. So most of the mass and matter is actually coming from Einstein. It has nothing to do with the Higgs. So the next time your particle buddies say they know the origin of mass in the universe, you tell them otherwise. But this also brings to the point that the Higgs mechanism was actually first introduced in the context of superconductivity. And this was introduced by Anderson, who was trying to look at what happens when you put a superconductor in a magnetic field. And in going through that particular problem, he comes up with the solution that a gauge field, the one that gives rise to photons, gives a particle which actually has some mass. So this was his Anderson mechanism for how a photon acquires mass in a superconductor. And then a few years later, actually 1 year later, you see this paper by Peter Higgs, which gives us the Higgs mechanism for the way the W in the boson would acquire mass. He says that this phenomenon is just a relativistic analog of plasmon phenomena to which Anderson, in this paper, has drawn attention. So it's a great example in history where condensed matter has been able to contribute to much bigger questions of the cosmos and the origins of the universe. And as we move forward, and we're going now from conventional electronic matter, things like metals, conventional superconductors and semiconductors and band insulators, to more exotic things, there is now more potential in which we can try to make these connections. So here are a few examples how you can try to make connection between the cosmos and what you can study in the laboratory. We have a lot of systems in which we can start to study the quantum phase transitions in a cryostat downstairs in the basement. And perhaps those ideas can lend valuable information about how the phase transitions in the early universe happen, how you get the 4 fundamental forces of nature, for example. If you look at entangled systems, something that we actually have a very hard time measuring in condensed matter, how do you measure entanglement? There are a lot of these ideas in quantum gravity. For example, measuring entanglement entropy in quantum gravity has a formula which is related to how you measure that, has an area formula which is related to how you measure the entropy of a black hole. So then there seems to be some relationship between the geometry of space-time and entanglement. So then one can feed back again on that. If you look at fractional quantum Hall states, which are topological phases of matter, and you look at the chiral states that go around them, they're described by something called a chiral conformal field theory, and these were first introduced in string theory. However, we can really easily study fractional quantum Hall effect downstairs in the basement. So once again, you have the idea of strings theory in terms of the theory that they have and something that we can do in the basement, and those two can feed off one another. So I want to move to high temperature superconductivity. This is a system which actually exhibits quantum criticality, potentially exhibits this topological phases, has the unconventional superconductivity in there. And over the last 30 years, it's yielded a lot of great physics, and actually it's one of my great passions to continue to work on this particular, in this particular field. But let's take a step back again, and if you look at the discovery of superconductivity back in the early 1900s, and then the successive observations of other superconductors in which their transition temperatures are slowly starting to rise. So here's liquid helium temperature. Here's liquid nitrogen temperature. And one would think, oh, well, if I continued along that path by the year 3000, I would have a room temperature superconductor. Well, that's a long time to wait, but we did learn a lot. We learned about how the importance of phonons in mediating the superconductivity, phenomenological descriptions in terms of Ginsburg-Landau, and then finally the BCS theory of superconductivity. A little bit in the late 1970s, early 1980s, come along these heavy fermion superconductors. They look like they have very, very low superconducting transition temperatures. If you normalize by their Fermi temperature, they're kind of high temperature superconductors. But the real progress comes in the mid-1980s with the discovery of the cuprates, these lanthanum-based cuprates. And very quickly, you have the discovery of new compounds in which the transition temperature rises very, very quickly. You're like, great, by the year 2000, I'll have a room temperature superconductor. Of course, we all know that did not happen. And one of the reasons is, and we've plateaued in these fields, is that we really just don't understand what the mechanism for high temperature superconductivity is. And once I show you the phase diagram, there's all these intervening phases which make it difficult to even understand what is contributing to superconductivity, what is suppressing it, what is enhancing it. And in 2008, we have the discovery of the iron-based superconductors. And the hope is that perhaps there's some similarity between these compounds and these compounds, and even maybe these compounds. There's some universality which will allow us to engineer a room temperature superconductor. I have to put up one of these pictures. Of all the possible applications one can have with high temperature superconductivity, I'll skip that for now. We can talk about that later. But the basis for the cuprates lies in this structure here. You have copper atoms surrounded by oxygen atoms. And once they hybridize, what you really have is one electron left in the dx squared minus y squared orbital. And you look at that as a half-filled band. You said this should be a metal. It turns out it's not a metal. It's what we call a MOTT insulator. And the reason for that is that the Coulombic repulsion on any given copper site, when you try to doubly occupy it, is so huge that it suppresses that motion. And so what you really have is an insulator. And in fact, you have an antiferromagnetic insulator. But what you could do is if you could put in holes into the system. You can remove an electron. And now the electrons can move. So now you have some mobility in the system. And you also have the fact that you have this antiferromagnetism. And this very much looks like what you would have for pairing, taking two fermions and pairing them to make a Cooper pair. So you have Cooper pairing, what looks to be like Cooper pairing, and the exchange interaction is actually quite high. The scale is about 1,000 Kelvin. And now they're mobile. So this seems to be a nice platform which you can have a 1,000 Kelvin superconductor. But you don't. What you really have, as you see in this phase diagram, is that once you start to put holes in, which is described by P, you enter this pseudogap phase. And superconductivity only really sets in once you pass 5% doping. And even the highest temperatures will be somewhere around 140 Kelvin, nothing up at 1,000 Kelvin up here. So this is why we don't understand what is in these compounds. And to make it worse, they seem to introduce certain objects that we find quite mysterious. For example, if you look in the pseudogap phase and look at photoemission spectroscopy and try to look for a Fermi surface, you don't find a Fermi surface. You see these open arcs. So there isn't even a closed contour when you're in the pseudogap regime. If you keep doping the system and get to this side, you do find that eventually it does close. But the question is, what is this object here which doesn't have a closed Fermi surface? So we're left with the questions, what is the electronic structure of the pseudogap state? What is that thing that shows up when you keep doping the system and expect a 1,000 Kelvin superconductor, but it doesn't appear? Does this pseudogap play with superconductivity? And even more fundamentally, what are the forces that pull electrons together to form Cooper pairs? Early on, though, when I showed you that phase diagram, there was evidence for additional broken symmetries in the system. So in the mid-1990s, neutrons and X-ray measurements show that there's actually, in the lanthanum compounds, they show that there's this very odd structure in the copper oxide plane where you had these rivers of mobile charge, and then you had this antiferromagnetic insulator. So it looks like you've broken translational symmetry in that direction. A little bit later, STM shows in their measurements that the system really does have a modulated electronic structure. One of the earliest experiments actually was done by Jennifer Hoffman back at Berkeley, where they look at superconducting vortices, and inside those vortices they see this modulated electronic structure. And then this was confirmed in the normal state and also in the oxychloride family of the cuprates. Finally, in the last 5 to 10 years, scattering probes have found that, in fact, that broken symmetry state seems to constitute a dome in the phase diagram. So it seems to be something much more prevalent than maybe an oddity in the system. So now we recast our questions. What is the relationship between this zero gap phase and this density wave, and then this density wave to the superconductor? And what I'm going to show you initially is just a quick recap of my own work on the density wave phenomena, and then try to find if there's a relationship between all three of these through something else that we call a paired density wave. So my own work was to look at the density wave as seen by STM at a particular energy scale. So STM can measure the electronic structure at any particular energy. And when we looked at energies which were related to this pseudo gap, we found this very peculiar ladder-like structure. Actually, this observation was made well before I got to the scene. I started to do the analysis on this to see if there's actually any additional structure that we didn't know about before. Let me give you a closer look at that. So here are those ladder-like patterns. I'm going to zoom in. And now I'm going to superpose the atomic lattice. So here are copper atoms in black and oxygens in blue. And what you see, for example, in this unit cell here is that the oxygens in this direction are dark, but the oxygens in this direction are bright. So there seems to be an internal structure to this broken symmetry state. So it's got a 4-unit cell periodicity, and there seems to be an internal structure to it as well. Well, what we really found out, and Subir was the first one to propose that in fact these objects could be what we call a D-symmetry density wave, or a D-form factor density wave. They are ones in which, if you look at the oxygens in this direction and then look at the oxygens in this direction, they are modulating in antiphase. So one is going as a cosine, and the other one is going as a negative cosine. So the modulations are actually exactly out of phase with one another. We don't understand how this arises. There are theories for it, but it doesn't seem to all mesh with everything else that we know. You have to really force in the models to get a D-symmetry density wave to come out. This is just a topograph of a large field of view with these ladder patterns in them. Through some special analysis techniques, we can find that actually the periodicity is about 4-unit cells, as I've shown here. And this is going to become important later because I want to relate this structure to the paired density wave structure that I'll show you later. Something very peculiar about this density wave is that if you were to take a crayon and then color parts of the field of view in which the density wave runs in this direction, so you can see these stripes, and it runs in the opposite, the perpendicular direction, you can start to color that field of view and you get this very disordered pattern. So whatever is generating the density wave, it's not doing it as a long-range density wave. There seems to be something pinning disorder into the system. It might be intrinsic. It might be due to impurities. We don't know yet. But it is something that's rather disordered. And furthermore, when Jennifer Hoffman looked at vortices and saw the periodic spatial modulation, we went back and looked and saw, in fact, within the vortex cores, this is I'm just showing the amplitude of these modulations, there really is one of these D-symmetry density waves inside them. And furthermore, oddly enough, and we can't explain this part yet, if you were to look at a density wave inside a vortex core here and then one here, they're perfectly in phase with one another. So if I were to follow the modulation, it perfectly matches up with this one. Even though they're 10 nanometers apart, there seems to be some information which makes the phase, spatial phase of this one and this one match up. So there's something underneath all that which is coordinating the system. Well, all these broken symmetries led Emery, Kivelson, and Fratkin to propose this, that perhaps liquid crystal states, which we, for example, have in our phones, can also be seen in electronic systems. So they have a theory in which an electronic liquid, one found in a metal, for example, but in this case, they do it for a MOTT insulator, something that's very strongly interacting, so correlated, that in these systems, one can actually get the same kinds of patterns as you would have in a liquid crystal. So if there are no broken symmetries, you just get this isotropic fluid-like object. If you break rotational symmetry, you get something called a nematic, but you preserve translational symmetry and reflection symmetry. A smectic will break translational symmetry in one direction, and then the crystal, so now you have a solid, breaks translational symmetry in both directions. So this is a situation where the electron fluid itself actually behaves like a regular liquid crystal and can acquire any of these forms. So they were proposing that these broken translational symmetries that we're seeing in the cuprates, for example, are coming from a theory which gives you this in a strongly interacting system. So in STM, electronic smectics have been observed, as well as electronic pneumatics. This is in the cuprates. This is in the iron-based compounds. So we know that they're there. They're very strong. But now if you take these orders, which in some sense are classical orders, you're breaking point group symmetries, and then you combine them with quantum orders, such as magnetism and superconductivity, you can give rise to some kind of new order, which, for example, would be a pair density wave. The question is, what is a pair density wave? And this really goes back to the 1960s. This first idea was first proposed by Fulda, Farrell, Larkin, and Ovchinnikov, who said, what if you took a superconductor and you put it in a very strong magnetic field, such that you split the Fermi surface between the up and the down states. So usually we have up and down at equal energies pairing to make Cooper pairs. But if you now lift one Fermi surface relative to the other one, you can't pair minus k and k to make that Cooper pair anymore. Now you have to make some different kind of states. And in that scenario, you take a k in the up state, and you take a minus k plus q in the down state, and those are the ones that can pair. And then in contrast to regular Cooper pairs, this Cooper pair has a center of mass momentum which is no longer 0. It actually has some non-zero value, which is equal to q. And in this scenario, the superfluid state's order parameter, or you can think about it as the gap function, is going to modulate in space. So this is what we call, this is a part of the family of the pair density waves in which the order parameter of the superfluid, that phase which breaks the U1 gauge symmetry, has a spatially modulated signature. And just to bring it back, there are also theories in quantum chromodynamics how you can get one of these pair density waves in a compact star. So good connections. So the question is this thing we saw with regular STM tunneling possibly coming from a pair density wave state, a modulated superfluid state? But the difference being that when the 1960s version was proposed, it was in a magnetic field. Is it possible that in the cuprates there's a self-assembled one, that you don't need a magnetic field, that it spontaneously emerges because it's trying to mix the quantum orders and the classical orders of the electronic liquid crystals and the superconductivity? So there's lots of evidence. The same people that proposed these electronic liquid crystals looked at the lanthanum-based compounds and saw that this cascade of transitions that happens in these lanthanum-based compounds could be explained if the layers, the copper-oxygen layers in those compounds had a modulated superfluid, but which were orthogonally oriented. Observation of angle of resolve photoemission shows that when the gap opens up, for example, for the density wave state in that dome, ARPAS can make that measurement, the gap doesn't open at the same k as the Fermi surface intersected the Fermi level. That k seems to shift. And that's odd. A density wave shouldn't do that. And this led Patrick Lead to propose that perhaps one can explain this phenomena by proposing that it is a pair density wave. So he comes up with a mechanism by which, without a magnetic field, you can get k up and minus k plus q down to pair to give rise to a pair density wave in the system. And he even comes up with a phase diagram for it. So here you have this pair density wave which is incoherent. There's no phase associated yet. There's just Cooper pairs that are trying to bind. They're kind of modulating, but there's no phase stiffness to the system. You get down, you get the charge density wave, and eventually you get down to D-wave superconductivity. And along that, there's a whole slew of other proposals for the fact that there could be a pair density wave in these systems. So how would you actually really check for a pair density wave? You have a modulated superfluid state, and you want to check directly that it's there. Here's where we appeal to Josephson tunneling. If you have two superconductors, so here's superconductor 1 and 2, each of them has their macroscopic quantum phase. And if there's any difference between these two phases, when you bring them into sufficiently close contact, a current's going to start to flow without you having to apply any voltage. And the maximal current that can flow is set by this I sub j, which we call the Josephson critical current. So you see here, for example, if I try to push current, so I can put also a current source here, and I can try to push current through the system. no voltage will appear across this junction. So here's the current increasing, no voltage across the junction until you hit the critical current, and then you become normal. And then you go on to your normal branches. And by measuring that critical current, you actually have a measure of the superfluid density or a measure of the condensate order parameter. So what we really want to do is to measure that quantity with a scanning probe so that we can see the spatial structure of the superconducting order parameter. And this ends up being a rather challenging thing to do because, well, we want to maximize I sub j. If you maximize the critical current, then you can have a better signal on which to grab. But if you're trying to do it with a scanning probe where you're trying to get that probe size to be on the nanometer scale, Ij scales as the cross-sectional area of the Josephson junction divided by the distance between the two superconductors. So the smaller you make your probe, the smaller that's going to become. And then there's also temperature dependence on how I sub j will evolve. So if you have very low temperatures, you'll have a bigger I sub j than when it's very low. And when you put it all together, the constraints end up being that, so this for STM on the CUPRATES is what we call a normal junction resistance. This is actually a very low junction resistance for STM on the CUPRATES. It means also that when you create a superconducting tip, so now you need the tip to make the Josephson, a tip to be superconducting to make it a Josephson junction. You want that tip superconductor to be about as strong as the one as your sample, and you got to get to below 100 millikelvin. Okay, so first challenge, make the tip a superconductor. And you say, well, that's kind of easy. You pick up a metal, which is a superconductor. Well, the problem isn't, if you pick up a metal, let's say you pick up lead, that has, in the low kelvins, that's its transition temperature. So that makes it more difficult. You want a superconductor who has a very high transition temperature. So we developed a recipe by taking a regular tungsten tip and very elegantly jamming it into the surface and picking up a flake of bisco. And it turns out that that flake on top of the tungsten ends up being a superconducting tip. So now you can actually create a Josephson junction between your tip and your sample. And this is particularly important for another reason. One is that if you had taken a lead tip and gone on the CUPRATES, which are D-wave superconductors, and used an S-wave tip, there's no guarantee that those Cooper pairs from an S-wave tip will tunnel into the Cooper pairs of a D-wave sample. So now we have D-wave in both. Of course, if you're going to make a Josephson junction, which means you're going to bring your tip very, very close, you don't want any vibrations to keep jamming into your surface. So you have to create a very stable environment in which for this to happen. So if you go to the basement in Jenny Hoffman's lab, she has a room like this. This is a replica of something at Cornell where I did these measurements. This is a floating room where you have a 30-ton block of concrete sitting on 6 air springs, and you have an acoustic room here, and then there's actually another acoustic room on the outside. On the inside, you have this massive tripod, which is several tons by itself, sitting on air springs. You cool the whole thing on this custom-designed millikelvin dilution refrigerator. And by the time you get down to where the tip is, the mean motion of the tip per root Hertz is in the tens of femtometers. So you have a very stable tip where you can form the junction, take your measurement, and then move over and take another measurement. One thing I didn't realize when I was presenting this to people, I said, oh, well, it's easy. You make the superconducting tip, and then you're done. Well, it turns out you can actually operate in 2 modes, right? If you pull the tip far back, you don't have a Josephson junction anymore. What you do is you have a superconducting tip. You try to push a Cooper pair through, but its wave function doesn't overlap sufficiently with the sample, so it breaks the Cooper pair apart, and then you have regular STM tunneling again. What you really need to do is to push this tip in pretty far, such that the overlap between these 2 wave functions allows for a Cooper pair to tunnel between the 2. This is the Josephson regime in which one can actually tunnel Cooper pairs. And this is the normal tunneling regime. And we're actually going to use both. This is actually important for our studies. So here's a topograph taken with our superconducting tip. And you're like, that's great. It looks like you have atomic resolution. Well, keep in mind our tip is probably about a nanometer big. And what you're really seeing is that the tip has a crystal on it, right? And has an atomic lattice. And then here's your sample. And as you raster your tip across your sample, there's going to be highs and lows between the 2. And that's why you see what looks to be an atomic corrugation. We can tell it's about a nanometer resolution because if you look at the variations, and we know that this is there in the CUPRATES, these dark and bright spots are about a nanometer nanometer big. So we think the resolution of the tip is on the order of a nanometer in this case. This is the circuit for this scanned Josephson. Here's your voltage source that we're going to turn into a current source by putting a resistor here. This is your tip, and this is your sample. And now this is a Josephson junction. We can model it as this circuit element. It turns out because the junction is so small, it's a nanometer-sized junction, it's no longer a coherent Josephson junction. And there are some very smart people in Russia who worked out what are the characteristics of a nanoscale Josephson junction, which works in this what we call a phase diffusion regime, where as you inject the Cooper pair, its energy changes a little bit and you can emit a photon, for example. So they found out that in that case, the IV characteristics are not directly proportional to the critical current, but to the square of the critical current. So for example, this is a set of curves for different, what you could think of as different tip distances as what you would expect for the IV characteristics. And in that theory, it shows that the peak still, if you were able to measure the peak of this curve, what you're really measuring is the critical current squared. And some pioneering work was really done by Bob Dines in UC San Diego, where he took actually a lead tip and he brought it very close to BISCO and almost was touching it. So he did like almost a point contact measurement and was able to measure these particular curves here. He does state in that paper, using an S-wave tip, what he was probably seeing was some distortion of the crystal lattice, which gives rise to a bit of S-wave superconductivity in the system. That was his explanation. We're still not quite sure to what extent S-wave to D-wave can couple or not. But what he was unable to do is, because he had to jam the tip into the surface to get that, is like he couldn't scan. He couldn't actually move the tip and start to look at these curves as a function of spatial position. So for our circuit, where we put in this little resistor, and this is our voltage source, we would expect to get this. So we took the old formula and just added one of these, and we got that. And if you were just to remove that slope, which is coming from the fact that you have this resistor, you end up with a curve like this. And if you measure what's at the top, this ij squared will pop out. And so this is the data. So the red is a forward sweep in the current. So you're pushing current through the system in one direction, and blue is pushing it back in the other direction. And here we've removed the slope. There's still a little bit left. We think that depending on how incoherent the junction is, you'll always have a little bit of the slope left over. But effectively, now that you have this set of curves, what you can do is look for the maximum value. And by looking at the maximum value, and I'm calling it I sub c, this is proportional to the critical current squared, which itself is now proportional to the square of the order parameter. Okay, so here is in regular tunneling mode, we pull the tip back, take a topographic image, and in that same field of view, you want to measure these curves at every spatial location and extract that peak height. And that'll give you I sub j squared as a function of position. And when you do that, that's what you get. Well, you said, okay, well, is this really a measure of the superfluid density or the order parameter in the system? And the way to find that out is, well, you want an on and off switch. If you could turn the superfluid on and off and then see how that image responds, then that would be a good answer. Well, luckily nature was kind to us and it gave us zinc atoms. It was shown a long time ago that if you put a zinc atom into the CUPRATES, very locally it punches a hole in the superfluid. It suppresses the superfluid density and creates sort of this Swiss cheese model, Swiss cheese of the superfluid. So now we go back into our single tunneling mode, and we can image where the zinc atoms are. So high is black here. So intense peaks are the zinc atoms. And then we, in the same field of view, create that image. And you see for every place there is a zinc atom, there is a suppression of the IC map. So this was our way to validate that this IC measurement is really a measurement of the superfluid density. Now, if there were a pair density wave in the system, what would you expect? Well, if the order parameter had a uniform component and then a modulating component, then there is this Amogocar-Beretov relationship which relates the critical current to delta. That would tell you that the critical current should also then have a modulating component to it as well. Well, you can already see by eye there's some modulations in the system, but we always like to take Fourier transforms. And when you take a Fourier transform, it becomes very obvious that there are 4 peaks which represent a 4-unit cell modulation in both directions in this modulated superfluid. And here's that image I showed you earlier on. This was the modulation of the electronic structure measured by STM in those ladder patterns. It turns out that the Q vector, the modulation wave vector of this object and this object, are very, very close. That leads us to ask, well, is it possible that the charge order is modulating the superfluid? Or is it that you have a pair density wave, which then gives rise to a charge density wave in the system? And that's something that we actually still have to find out. And that's going to require to do some more doping-dependent studies. It's going to require some more theoretical work. And one of the smoking gun piece of evidence, which we hope to find, I showed you a 4-unit cell modulated Cooper pair density wave. Is it possible that it's not really 4-unit cell, but 8-unit cell? So think about that for a moment. Our probe can only measure the amplitude of the superfluid. What if there was a phase component that went along with it? You could have the amplitude being 4-unit cells, but if the phase were 8-unit cells, you wouldn't be able to see it with this technique just yet. So in trying to move towards a scanned Josephson system in which you're also sensitive to the phase, would also be able to answer this question. But we also do have recent theoretical work with people down in Florida who are able to relate that this object may actually be coming from an 8-unit cell pair density wave. So now we're trying to actually see whether these two sing together in the 8-unit cell pair density wave scenario. So I hope I've been able to show you that once you create a new modality for imaging something and being able to directly engage with it, one can really learn a whole new set of characteristics from the system. And in this case, what we've been able to do is to look at the spatial structure of a superfluid. And as we move forward and as we try to engineer new condensates, this kind of probe is going to become very important to see whether we're actually achieving what we're setting out to do. But at the same time, there's a lot of new exotic systems like topological superconductors who have their own intrinsic superconducting structure. And this probe, once again, would be very, very helpful in that endeavor. And with that, I'd like to thank you. Questions?
Questions? I have a question. How, with the visco flake and all that, what's the technique that you use?
So what we found out actually is if you take the tungsten tip and start to do field emission on gold to get it blunt, you blunt the tip, and then you go onto the visco and start to scan at very low or very small distances. Small fluctuations will dip the tip, and you can actually pick a flake up. So I would say that the success rates on it's. I guess yeah, I think so. Yeah, you can't scan over that part again. As soon as you as an STM operator, you sort of sit there and you look at your screen, and as soon as there's a change, you stop everything. You pull the tip back, and then you move far away, and you land. And that topograph that I showed you, which looked like perfectly periodic, was a really telltale sign that you had picked up one of these really nice. So I'd say the success rate once you did the proper field emission on gold is somewhere between 10 to 20%. It's not bad. Yeah, yeah.
Does it make a difference if you rotate the sample for it? Right?
That's an excellent. Yeah. So we never got to the rotation. We know, but what I will point out is that we know that it's not rotated. Because if you have one crystal structure rotated to the other one and you were to scan, you would have a moire pattern. You would have essentially an interference pattern between the two. And we don't get that. So once again, Mother Nature has been very kind that once we pick it up, it nicely registers itself to the lattice. It rotates itself exactly back into the lattice. Yeah. But you're right. It would be an excellent experiment to actually even see how the IC signal would change as you rotated the sample.
You are not able to tunnel, or it's not. You said it's not clear, right?
So theoretically, you shouldn't be able to tunnel into that. But whether you can tunnel in and then the Cooper pairs reform somehow, or in the case of the experiments where you have slight distortions of the unit cell, that allows you to have a slight S-wave component on top of your D component.
Could this be a measurement to measure the order parameter of nictides or something?
Yes, definitely, right.
So if you take a D-wave tip and then put it on a nictide,
yes.
would you?
Well, so I think the next thing to do is to take an S-wave tip and with this technique and try to scan again and see how much of the signal we get back. And that could be, and then once we know that, maybe that would prove that if you took a D-wave tip and went to the nictides and we got a signal, then that would be quite telling.
One last question? Okay, if not, let's thank you.
Thanks very much.